Today we're going to be beginning chapter 12. Section 1 is an introduction to limits. We have talked about these briefly in the past. Now we're going to actually talk a little bit more in depth about what they are and how we can evaluate them. Before we do that though, just a quick little reminder, a little blast from the past. We've got a warm-up question here. Actually, two. So on the left, we have two functions, f of x equals x squared plus 1, and g of x equals the square root of x plus 1. Go ahead right now and find both composite functions, f of g of x and g of f of x. You can pause the video and then come back and see if you match me. All right, so composite function for f of g of x is going to be the square root of x plus 1 squared plus 1, or x plus 1 plus 1, or x plus 2. And then the opposite composition, g of f of x, is going to be the square root of x squared plus 1 plus 1, or the square root of x squared plus 2. All right, so we take our original input of x in the outside function and we replace that with the new input of our, inside function, g of x or f of x. All right, second review is one we've been doing quite often, or at least we've been doing it for a long time. That's our difference quotient right here. And this is something we want to make sure that we're keeping on top of, and we remember how to do this. So we've got our function f of x equals x squared plus 1, and we want to find and simplify our difference quotient. So f of x plus h minus f of x over h. Remember, this is saying that h then can't equal 0. So substituting in, we have x plus h squared plus 1 minus x squared plus 1 over h, which gives you x squared plus 2xh plus h squared plus 1 minus x squared minus 1, still all over h. We can start canceling some things in the numerator so that x squared and the negative x squared cancel, 1 and negative 1 cancel, and so we are left with 2xh plus h squared over h. Factoring an h in the numerator out, we get 2x plus h times the h over h. H's cancel, and we get simplified difference quotient is 2x plus h. So we've been doing that all year. Hopefully you remember how to do that. And then if you're writing this out, we remember you have to have these parentheses or brackets around that second function so that that negative gets distributed correctly. All right, so quick little reminders of things we've done in the past and that we're actually going to use again in this next unit. All right, so we're going to do this introduction to limits. So this is the very beginning of our calculus. This is something that you're going to utilize quite often next year in calculus. And we're going to start by talking about what a derivative is. And we're not going to do much with it today, but we're going to talk about what it is, and then we're going to get into the limits. And the limits are going to come back into play when we look more detailed into derivatives in the next couple days. But a derivative is an instantaneous rate of change of a function. All right, so it is a rate of change, sort of like a slope. It's a rate of change. How fast or slow is something changing, but it is instantaneous. So if you think about the slope of a line, that's a constant rate of change across the whole function. Every single point has the same rate of change on that function, on that line equation. A derivative isn't necessarily going to apply to every point along your function or along your equation, but if you look at just one single point, one single location on your equation, at that exact location, what is your rate of change? That is your derivative. Okay, so that's one way to think about it. Another way is to think about your slope of what's called a tangent line. And you would have talked about tangent lines at least a little bit in geometry. A tangent line is a line that has one shared point in common. So what happens is, okay, if I say I've got this point right here on my equation, on my graph, this is my parabola, my quadratic function here. My tangent line is going to share that one point and that one point only. Now, it might end up crossing over later on depending on what the function looks like, but at that in that particular region, it only has that one point. So this red line that I've just drawn is tangent to my graph at that particular point, which is what? 0.4, 6. So that one single point is shared between both my quadratic, my parabola, and my tangent line. And so it just brushes up right next to it. So if I wanted to think about in terms of the quadratic, in terms of my parabola, my derivative at this point, it's going to be the instantaneous rate of change of that graph. How quickly is that graph increasing or decreasing at that point? That's going to match the slope of this tangent line. So the derivative, we can think of it as the instantaneous rate of change or the slope of the tangent line at one given point. We can't look at it for all the points together, at least not right now. But if I take just one point, I can find the tangent line and say, well, the slope of that tangent line is going to be the instantaneous rate of change at that point. That is what we call our derivative. And you can see if I pick a different point, let's say if I pick this point up here at the top, and this is 1.2, I think, a little over 9. So we're going to say it's about 9.2-ish. That's an estimate because I don't know what this equation exactly is. But if I were to look at this tangent line, and check that one a little better, you can see how this tangent line here up at the top is going to have a different slope than that tangent line. And so if you're looking at the derivative at those 2 points, they're going to be different from each other because the instantaneous rate of changes are different. Here, my rate of change is going to be larger than my rate of change is here. If I think about slope rise over run, okay? So derivative, there's 2 different ways we can talk about it right now. When you're in calculus, you talk about it a couple other ways. But the derivative is your instantaneous rate of change. How quickly is your function changing at one particular point, which you can also think of as the slope of your tangent line at that one particular point. Okay. So we're going to get back to what a derivative is and how we find a derivative. But before we do that, we actually need to talk more about a limit. All right, so we have mentioned these briefly in the past. So we had those summation formulas. Some of them had limits in them. We talked about limits with eccentricity for our conic sections, but we didn't really talk about how to find a limit or the definition of a limit. So a limit, its formal definition is what we have here. It's essentially, well, this isn't quite the formal definition, but it's a little bit more formal than we'll probably use. But it essentially is, okay, you have some function. Okay, we have some equation, we have some graph, we have some function f of x. What we want to do is we want to let x, our input variable, move. And we're going to let x move along that horizontal. And as x moves along the horizontal, as x moves this way, my y values are moving along my graph. You see, okay, so my y values aren't just going up and down, but those output values are moving along this graph here. So what we're going to do is we're going to let our x value, our input value, get really close to some number. And I don't want to define my limit to just work for a single number. So we're using c, an arbitrary number. So c is somewhere. C is an x value somewhere. And what we're saying is, okay, we're going to let x get really close to c. So let's say this is my c value here. Let's say this is c. We're going to let x get really close to c from the left and from the right because we want it to come from both directions, from either side here. And then we're going to look at what happens to our y values as x is doing that. As my x value is getting really close to c, okay, this is when my x is equal to c here, and I just picked a random point, this could go anywhere. I'm going to look, okay, now my y values, they're traveling along that equation. I want to say, okay, what y value or what f of x value are we getting close to? And we might not actually hit it, and I'll talk about that in a little bit later, but which one are we getting close to? All right, so in this definition, it says, if f of x becomes arbitrary close to a unique number L, as x approaches c from either side, then we would say the limit of f of x as x approaches c is L. So, or we could write it out this way. You could say the limit as x approaches c of f of x equals L. So essentially, as x gets close to c, oops, my c turned into an O there. As x gets close to c, what does f of x get close to? And close to could mean be right on it, could mean it hits it. Doesn't necessarily mean that though. And we'll get into that in just a little bit. But as x gets close to c, what does f of x get close to? Now, this is the notation that we're going to use. It's what you're going to see on WebAssign. It's what I'm going to require, what Mr. Blake is going to require on anything that you write and turn into either of us. We're going to see this notation. So, a couple things about that notation. Lim fx is nonsense. I ran out of space. There we go. Is nonsense. That means nothing. I need to know the limit as x approaches what? I have to have something underneath that limit notation that tells me what is x getting close to. It could be a number like 7 or 2 or 0. It could be infinity. That's fine, but I need to have something there. Okay. If I were to write the limit as x approaches, say, 0, and I just write that, that is also nonsense. I need to have an input function. I need to know what I'm taking the limit of. If I just say the limit as x approaches 0, that's okay, x is getting close to 0, but what function am I looking at? What y values am I going to use to determine my limit? I need to have a function. All right, so when I'm looking at limit notation, as I'm writing it, as I'm reading it, I need to have the value that x is approaching, the value that x is getting close to, and I need to have a function to evaluate the limit on. Right? I need both of those things in my notation. All right, so what we're going to do is we're going to evaluate some limits a couple different ways. The first one we're going to do is with direct substitution, and this is always the one you want to try first. This is by far the easiest way to evaluate a limit. And if you're allowed to do it, if you have a function that this works on it, that is fantastic. It won't always work, but this is the one that we want to try first. All right. So if I think about this equation here, if I wanted to know as x gets close to c, what is f of x equals? This is just f of c. I have a continuous function here. My continuous function means there's no holes, there's no gaps, there's no jumps. In this particular function, even though I don't have the equation, there's no domain restrictions, at least not at c. I don't have a domain restriction with my c value there. So it is just the limit is going to end up being equal to my function value. So when I look at this equation, this limit expression that I have here, the limit as x approaches 3 of the function x plus 3. If I were to do this on my graph here, okay, here's my x equals 3 down there. If I were to approach from the left and from the right, because I have to do it from both sides, there's no issue about this point. It's not an open circle, there's not an asymptote or anything like that. It is a continuous function. So this is going to just equal 3 plus 3 or 6. My f of 3 is 3 plus 3. So direct substitution is the nicest, the one you always want to try first. Because your limit, if you can use direct substitution, is just going to be your function output. As x gets close to 3 from both the left and from the right, my y values get close to 6. So the limit as x approaches 3 of x plus 3 is 6. Now, direct substitution does not work on every single function or every single limit. If I look down here, if I wanted to evaluate this limit, if I tried direct substitution, okay, we're going to see an issue. If we try that, I'm going to have 0 over the square root of 0 plus 1 minus 1, which is 0 over the square root of 1 minus 1, which is 0 over 1 minus 1, which is 0 over 0, and that is what we call undefined. That's not a number. If I put 0 over 0 in my calculator is going to get all mad at me and says, you can't do that. So direct substitution in this equation does not work. Doesn't work. So what we do is we have a couple other methods we can do. One is we can look at a graph, which we're going to see later, or we can build a table. We can estimate a limit numerically, which is a fancy way of saying build a table. All right, I can't substitute in 0 directly because I get this undefined form. That does not mean it's equal to 0. It does not mean that there's a hole in my graph or that there's an asymptote necessarily. There could be, but that's not necessarily the case. But what I can do is I can build this table and I can still sort of figure out what's going on. Because remember, our limit definition does not say what is f of x equal when x equals c. It's what does f of x get close to as x gets close to c. So what we did is I built this table, and you can do this in your calculator if you put this function. Okay, this is my f of x function here, because remember it's the limit as x approaches 0 of a function. So that's my function. If I put that in my y equals, you can go to your table. First, you would want to change your table settings, but you can do all this. If you don't remember how to do it, find me, find Mr. Blake. We can talk you through that process. But you can build this table in your calculator. But what you want to do is you want to analyze those values. All right. So I'm looking at my x values first. Notice I've got c equals 0. That's right in the middle. The numbers on the left, negative 0.01, negative 0.001, negative 0.0001. Those are all to the left of x equals c, x equals 0, and they are getting closer and closer, right? We're taking little steps closer and closer and closer. And then if I look at these x values off to the right, same thing. I start off at 0.01 all the way at the end, and I'm getting closer and closer to 0 as I move inward. All right, so I'm looking at the numbers that are coming in towards 0 from both directions. And what I want to do is I now want to look at my output values. And I want to say, okay, what number, not necessarily looking at this function, but looking at the table values, what number makes sense to go in the middle, looking at those numbers in my y values. So comparing, I got 1.99499, and then I have 1.99950, which is slightly larger, and then 1.99995, which is slightly larger. And then I look on the left, going all the way over here, 2.00499, 2.0050, slightly smaller. 2.0005, slightly smaller. I want to see what number makes sense to smush right in there. 2. 2 makes sense to smush right in there. So my limit, as my x gets really, really close to 0 from both the left and the right of this function, is 2. Not necessarily if I plug 0 into the function, I get 2 back, but my y values are getting close to 2. They're getting close to 2. Not necessarily they hit 2, but they get close to it. So a limit, remember, a limit is what are we getting close to, not necessarily what do we hit. Sometimes it's what we hit. Direct substitution, it's what we hit. No domain issues, it's what we hit. But if it's what am I getting close to, that is what I'm really evaluating. All right, so that's a numerical estimate. We're building a table. Another way is to look at it graphically. So we've got the same equation here. All right, we're going to look at its graph. We're going to look at the graph here. And so if I look at my graph, we're evaluating the limit around x equals 0, when x is approaching 0. So what I want to do is I want to focus on the part of the graph where x is equal to 0. And I want to look at it coming from the left and coming from the right. So that's going to be this point right here, that region right there. And I want to approach on my graph from the left and from the right. I want to say, okay, my f of x value here is getting close to what when x is close to 0. That's what we're looking for. When x is close to 0, when x approaches 0, what is f of x? What is this function x over the square root of x plus 1 minus 1 get close to? And you can see on the graph how it looks like it's crossing over at 2. So again, just like we did with our table, we would say our limit here is 2. All right. If you're given an option, if direct substitution doesn't work and you're given an option, graphically tends to be faster than the table. Okay. There are some web assigned questions where you're going to have to fill in a table, so you're going to use the table method then. But if substitution doesn't work, graphically is your next fastest, or at least it generally tends to be the case. All right. Now, there are times when limits don't exist, when limits fail to exist. And whenever you have a limit that doesn't exist, we would say it doesn't exist, but then we have to say why. Why doesn't the limit exist? All right, we can't just say it doesn't exist. We have to explain why, because it's going to fail one of these different reasons. All right. Now, there are technically more reasons why you wouldn't necessarily have a limit exist, but we're not going to look at those. They don't happen very often. So we're going to look at just these 3 right here. Okay. So we can say that the limit of f of x as x approaches c does not exist, or we can write this: the limit as x approaches c of f of x does not exist, and we usually abbreviate it to DNE, does not exist, because of one of these 3 reasons. First reason, when you come at your x equals c value, whatever c value you're approaching, when you approach from the left and when you approach from the right, your function approaches 2 different y values. Okay, it says f of x approaches a different number from the right side than it approaches from the left side. So what's happening here is you have some sort of gap in your function. So this is typically, you're going to see these with those piecewise functions, not always, but typically with your piecewise functions. So let's say you've got something that looks like this. Let's say there's c. If I approach c from the left, I'm going to approach a positive y value. But if I approach it from the right, I'm going to approach a negative y value. Negatives and positives can't ever match. So the number I approach on the left doesn't match the number I approach from the right. So we would say left and right-handed limits don't match. That's another way we can say this. Left and right-handed limits don't match, or one-sided limits don't match. And we'll see some of the notation for that a little later. The second reason is that f of x increases or decreases without bound. Pretty much this is what we would think of as going off to infinity. My limit is infinity. All right, and sometimes we'll write that. We'll say the limit as x approaches c of f of x equals infinity. Now, when we say equals infinity, this is truly a does not exist, goes to infinity. that would be my reasoning. Sometimes we just say it equals infinity. So if you've ever seen the movie Mean Girls, at the end, when Caddy has her math Olympiads or whatever it is, and she says the limit does not exist, it's because, well, I actually can't remember that one, but I think it's because the limit goes to infinity. I could actually be wrong. I haven't seen that movie in a while. But she says the limit doesn't exist. So this could be something like, okay, let's look at this function, the function 1 over x squared. Looks like this. If I wanted to look at the limit as x approaches 0 of 1 over x squared, we would say this does not exist. It goes off to infinity. Because as I come from the left, I'm going to a positive infinity in my y values. As I go from the right, I go to a positive infinity in my y values. I never actually stop growing. As I pick those x values closer and closer to 0, my y values never stop growing. So they don't approach a number, but rather they approach infinity, so you'd say it doesn't exist. Okay, so it approaches without bound. The last one, we say f of x oscillates between two fixed values as x approaches 0. Oscillates essentially means it jumps back and forth very, very quickly. Very, very quickly. So it doesn't really, it doesn't have a continuous graph necessarily, but it jumps so fast. So it looks something like this. And you see this generally in some trig functions. So it starts jumping so fast that it can't actually get a read on what is y approaching this positive or this negative. It keeps going back and forth between them over and over again. So there's certain trig functions or trig functions with certain input values that cause this oscillation. All right. Most of the time, even of these three, we're going to see 1 and 2 more often than we will 3, but 3 still does happen. So limits don't exist. When we say they don't exist, we have to, on anything that you write and turn into Mr. Blake or I, you have to tell us why they don't exist. Is it because the left and right-handed limits don't match? Is it that it goes off to infinity? Or is it because it goes off to negative infinity? Or does it oscillate? Okay, so there's some basic limit rules for direct substitution that we're going to look at right now. And this is generally when we have these nice, really nice functions. All right, but these are pretty much all direct substitution. The one that's the weirdest is actually this first one. B being a constant. So if I have a limit of a constant as x goes to what any number I want it to be, it's always going to be the constant back. And the way we can think about this is if you think about what b as a function graphed looks like. Okay, if b is just some function, it's going to be a horizontal line. This is my function, f of x equals some value for b. So what happens is my y values, my output, my f of x values, they never change. No matter what x is getting close to, f of x never changes. So my limit is still just going to be b. So this is going to look like something like, okay, the limit as x approaches 0 of 10, that's just 10. The limit as x approaches negative 5 of 10 is just 10. All right, so the limit as x approaches c of a constant value b is just b. All of these other functions, all of these other limits we have here, if I look at my functions for those limits, we have x to the nth root of x. All of those are nice functions that don't have domain restrictions, except for number 4 has a domain restriction, but 2 and 3, there's no domain restriction on x. X is that line y equals x or f of x equals x. So I'm just going to do a direct substitution. I'm going to substitute c in for my function. And same in number 3, the limit as x approaches c of x to the nth power. So n is some positive number n, so it's like positive integer, so it's like x to the 2nd or x to the 10th or x to the 4th. We're just going to substitute. We're all substitutions. The last one, we do have that restriction where if I'm going to do that direct substitution, I need to substitute in a value that actually works for my domain. It needs to be a c value that's in my domain of x. So it's the nth root of some c greater than 0. So we're restricting c in number 4. But it pretty much says, okay, if you're going to do a limit of a function, x needs to approach a number that it can actually approach. So if I wanted to do, say, the limit of the square root of x, and I said, look, as x approaches negative 4, That doesn't really make sense because my graph is this. So if -4 is out here, how's x going to approach it if there's no function to the left of 0? Like there's no function over here for x to travel along. So this doesn't really make any sense. I'm gonna even call it nonsense because of that -4 is not really in my domain. So you won't really see any of that. Some trig functions that we want to be that would work in this as well. So if I want to do the limit as x approaches pi of the function sine of x, we're going to do that substitution. We get 0 back. And so if we, think about the graph of this, sine looks like this. So I want to go close to 0, close to 0, close to pi on my graph there. You can see that output value is getting close to 0. And also that's what you get when you do direct substitution. Sine of pi is 0. If I do cosine as x approaches 0, here's my cosine wave. I've got x approaching 0 on the left, x approaching 0 on the right. You can see it's approaching that output value of 1, which is, again, direct substitution. Cosine of 0 is just 1. Okay, so you don't need to do both of these, either direct substitution or graphical. Direct substitution is always direct substitution is always what you want to try first. We do have some properties of limits. You can do some things with limits that are nice. So we're going to let the limit as x approaches c of the function f equal L. And then the limit as x approaches c of the function g equal k, just to make things a little bit easier. If I take a function f and I multiply it by a scalar, by a constant value b, then that's essentially like taking b and factoring it out in front of the limit. Okay, this is going to be b times the limit as x approaches c of f of x, or b times L. That's what we're doing. Number 2 is really nice if you can break your function into a sum or difference of other functions, essentially do them individually. Then you can add or subtract the limits together at the end. Okay, so if I wanted to do, say, like the limit as x approaches 0 of x plus x squared, and this isn't a great value, but that's fine. This is like the limit as x approaches 0 of x plus the limit as x approaches 0 of x squared. 0 plus 0 is 0. Not the best example because everything is 0, but that's okay. You can split it up. The same works for products. If it's a multiplication, you can do that as well. And you can do it for division as long as your denominator limit is not equal to 0. And the last one is the power. Okay, it's sort of just like a direct substitution in there. So we have these nice properties for our limits that we can use. All right, so we're going to do a couple practice problems. We're going to find some limits. We might have some ones that don't exist, and we have to explain why. So the first one here is the limit as x approaches 0 of the absolute value of x over x. And if you graph it, this is the graph that you get, which is what you want to do. Because if I try direct substitution, which is always what I want to try first, okay, then I have the limit as x approaches 0 of the absolute value of x over x. That would be the absolute value of 0 over 0, which is 0 over 0, which is undefined. Okay, so undefined, that means limit doesn't, I can't do direct substitution for my limit. So I can either go to my graph or I can go to a table. I'm going to look at my graph here. Okay, so what I want to do is, coming from the left, I want to say, okay, what are my y values getting close to? And you can see my y values are getting close to -1. But when I come from the right and I say, what are my y values getting close to? My y values are getting close to +1. They are +1, so they are close to +1. If you are +1, you're close to +1. And you can see that as I come from the left and as I come from the right, I do not approach the same value. So our answer to this would be does not exist right hand and left hand limits don't match. And there's actually a faster way to write that, and I'm going to show you. A right-handed limit, the notation for a right-handed limit is we would say, in this particular one, the limit as x approaches 0 from the right. How we distinguish that is we put a little plus sign in the top right corner, right above that 0. That's saying we're approaching 0 from the right-hand side. Okay, we're taking numbers that are bigger than 0 and we're getting closer and closer to 0. So the limit as x approaches 0 from the right of f of x over x equals 1. When I wanted to do the left hand, I'm going to say the limit as x approaches 0 from the left, I use a little negative sign. That equals negative 1. So this sentence that I have here, I can actually shorten that and I can say, okay, does not exist. And the reason it doesn't exist is I can say the limit as x approaches 0 from the right of the absolute value over x of x over x does not equal the limit as x approaches 0 from the left of the absolute value of x over x, which you may be like, I'll just write out the words. That notation is going to be really, really important, knowing how to read that and how to write that in calc. So I would practice that now so that you're really comfortable with that when you take calculus next year. But that's what we're saying. The limit from the right and the limit from the left don't match. So my limit doesn't exist. All right, this next one here, very similar, but notice we did change what x is approaching. We changed our c value. So now instead of approaching at 0, we're going to approach at negative 1. So again, I want to first try direct substitution. And I know you can probably see on the graph what it's going to be, but let's try this. If I did this, the limit as x approaches negative 1, and remember, I don't have anything up here, so I'm not saying from the left or from the right. I'm saying from both. If there's nothing here, it's from both directions, okay? Of absolute value of x over x, well, this would be negative 1, the absolute value of negative 1 over negative 1. Well, that's 1 over negative 1, which is negative 1. And direct substitution works. And again, if you looked on your graph, we're going to come from the left, we're going to come from the right. We're at negative 1, and so we're close to negative 1. My limit's negative 1. This one we've already talked about. That's just the example I used. Didn't remember it was later on. But this one, again, if we tried direct substitution, we're going to have an issue. This is going to give me the limit as x approaches 0 of 1 over x squared, 1 over 0 squared, which is 1 over 0, which is undefined. And that's the issue. I can't leave it as 1 over 0, so we're going to look at the graph then. And looking at the graph from the left, we're heading off to positive infinity. From the right, we're heading off to positive infinity. So we would say this does not exist, positive infinity. Or we could say positive infinity does not exist. I do not remember on WebAssign if they're going to want positive infinity or if they're going to want do not exist. But on anything that you write, you have to tell me both. You have to tell me it doesn't exist, and you have to tell me why. Okay, the other way that you could say this is that it's unbounded. That's the other way you could say it. It's unbounded. All right. This one, we're going to change our bounds again. This time, instead of approaching 0, we're going to approach negative 1. And again, we're going to try that direct substitution first. And this time when we do direct substitution, we're going to have 1 over negative 1 squared, or 1 over 1, which is just 1, and it works. So in the last two examples, if I start with approaching 0, it didn't work on either of them. We didn't have exist, or the direct substitution didn't work at least, because it created something that was undefined. It created in both of them a division by 0, which meant that there had been a domain restriction. So whenever you're trying to approach a value outside of the domain of your function, direct substitution won't work. As long as you're within the domain of your function, direct substitution will work, and that's your fastest way. All right, just a couple more. This one right here. Okay, we're going to try that direct substitution first. Again, if I do that, I have -1 squared plus -1 minus 6 over -1 plus 3, or 1 minus 1 minus 6 over 2, or -6 over 2, which is -3. And you can see on your graph, okay, when x is equal to -1 here, get close from the left, get close to the right, you can see that y value is -3. It's getting close to -3 because it actually hits -3. So there's my limit. This one right here, this is our last one. We're going to change that value we're approaching once again. So this time we're going to change it to -3. If I do that, if I try my direct substitution, I'm going to have -3 squared plus -3 minus 6 over -3 plus 3, which I don't even necessarily care what the numerator is. I know my denominator is 0. So I know my domain restriction is going to come into play, and I can't do direct substitution. But in order to figure out what's going next, because I don't necessarily need to graph this, I'm going to look at my numerator. If I do finish finding my numerator, I'm going to get that at 0. And I have this 0 over 0. And if we recall our rational functions that we talked about a long time ago, 0 over 0 means that there is most likely going to be a hole in my graph. It is a removable discontinuity. It is a removable 0. So what would have necessarily originally been an asymptote is now just a hole. So what I want to do is I want to simplify my function if possible. All right, and so while I do this, I'm going to have to keep my limit notation because I'm not getting rid of my limit just yet. But I want to simplify this function here. So I'm going to start by just writing the same function again. Limit as x approaches -3 of x squared plus x minus 6 over x plus 3. Well, I'm not evaluating my limit yet, but I can say that that's the same as the limit as x approaches -3 of factoring my numerator. I can get x plus 3 times x minus 2 over my denominator of x plus 3. Now, this is where it's going to get annoying. You have to continue to write this limit notation until you actually evaluate your limit. You cannot drop that early. Okay, so it's going to be annoying because you're going to keep writing limit as x approaches blah, blah, blah over and over and over again, but you cannot drop it until you actually evaluate your limit. And you will lose points. It will be marked incorrect if you do drop it early. Not just by me in this class, but in AP Calc next year. It's easy points to lose there. We don't want to lose those easy points. But I can say, okay, well, I'm still, simplifying my function here. Look what I can do with those x plus 3s. Those cancel. So now, well, this is still the same as the limit as x approaches -3 is x minus 2. That doesn't have any domain restrictions. So now I can try direct substitution again on the simplified function. If I do that, now as I actually evaluate with direct substitution, I can drop my notation and say this is -3 minus 2, which is -5. Now, we can't see that on our graph here, but if I were to graph it, that means that there is a hole, like I said before, on our graph. So if I were to graph this, and I'm going to do that really quickly up here, if I were to graph this, that means this function, our original function, looks almost identical to the line x minus 2. Except when I get to this thing, when x is negative 3, there is a hole on my graph. So I can't just substitute in because that's going to give me an issue. That gives me that domain restriction, 0 over 0. But if I look at it here with the hole, as I approach along my function here, my f of x, my f of negative 3 doesn't actually equal anything, but it is getting closer and closer to that negative 5. So even though the function doesn't equal anything, the limit as x approaches negative 3 of my function, I'm just going to call it f of x because I don't want to rewrite it all, that does exist. That does equal negative 5. My function doesn't exist there, but the limit does. Because remember, your limit is telling you what are you getting closer and closer and closer and closer to. Not necessarily what do you hit, because you might not hit anything, but what are you getting closer to? So my function gets really, really close to negative 5. Doesn't touch it, because it doesn't actually exist at that point. I've got a hole there, but it gets close to negative 5. So I'd say my limit of the function as x approaches negative 3 is negative 5. Okay, so when you have something like this, when you have this 0 over 0, typically we want to try to simplify your function. Now we saw the 0 over 0 before. We saw it here, and we didn't try to simplify because trying to simplify here is not going to actually go very well. That absolute value of x over x doesn't really go very well. And then if I look at my graph, you can see the reason why I'm having trouble isn't because it's a hole, but rather I have a jump. And I can't fix a jump discontinuity, so I can't make the limit exist there. And then the one we had up above a while ago, this one here, this one we also had 0 over 0. And I could try and simplify this algebraically, but that's significantly more work than just building my table is. This very last one that we've done, simplifying it, we've done problems like this numerous times. It's not too much work to simplify, and it's still going to be faster than graphing it or drawing a table, creating a table. Okay. All right, so you have WebAssign homework for this one. If you have any questions, please find me, let me know. Have a wonderful